In this video, we're gonna learn about Hasse diagram, lattice, chain, and antichain. Let's revise partial order relation. Any binary relation that is satisfying reflexive, antisymmetric, and transitive property that is called as a partial order relation. Now, if we try to represent our partial order relation in some another notation format, then that will be called as a poset. Poset stands for a partial order set, in which your partial order relation and set both combinedly represented, and that is called as a poset. For example, this is my set A, which is having element 1, 2, 3, 4. Relation is on AB such that A is less than equal to B, or A related with B in such a manner that A is less than equal to B, and relation is this. Then this can be represented in another format where A set and on set A there exists a partial order relation which is less than equal to, and this is called as a poset. Hasse diagram. It is also called as an ordering diagram, and Hasse diagram are used to represent only partial order relation. Now it is very easy to convert a directed graph of a relation on a set A to an equivalent Hasse diagram. What are the things which we have in the Hasse diagram are this thing. What makes Hasse diagram different from your directed graph? These are the 4 points. Therefore, while drawing a Hasse diagram, following point must be remembered. The first point is that the vertices in the Hasse diagram are denoted by points rather than circles. Since a partial order is reflexive, hence each vertex of A must be related to itself. That is, A, A pair is already present. So the edges from vertex to itself are deleted in Hasse diagram. Since a partial order is transitive, hence whenever we are having A related to B and B related to C, this type of elements are present, then we have A related to C. This is the transitive property we have. So we always try to remove or eliminate all edges that are implied by transitive property in Hasse diagram. That is, delete edges from A to C but retain the other two edges. If a vertex is connected to vertex B by an edge, then the vertex B appears above vertex A. For example, if you are having order pair A, B and there exists a relation A to B, in that we always try to write vertex A on the bottom part and B on the topmost part, and such that their edge is having no arrow in between them. Arrow may be omitted from edges in the Hasse diagram. The Hasse diagram is much simpler than the directed graph of the partial order. Let's take example how to draw Hasse diagram of your relation. My set is A, which is having element 4, 5, 6, 7. Relation R is such that there exists less than equal to relation in between two elements of your set. Means AB is the element of your relation such that A is less than equal to B. Then on that, what type of elements I will have? 4, 5, 4 is less than 6, 4, 6, 4 is less than 7, 4, 7, 4 is less than equal to 4. So that's why 4, 4. In the same way, we will have another element 5, 6, 5, 7, 5, 5. 6 is less than equal to 7, 6, 7. 6, 6 and 7, 7. These are all possible elements of your relation. If we try to draw your relation in the directed graph notation, we will get this graph. Now to convert this graph into Hasse diagram, what we have to do? We just have to, there are two methods. In first method, what we are doing, we are just trying to represent elements of your set, each and every element in the notation which is given to your relation in that format. So this is less than equal to operator. What we will do, we will try to write these elements in that relation format, in that notation format. Your 4 is less than equal to 5. Your 5 is less than equal to 6. Your 6 is less than equal to 7. Now we will try to draw edge in between these two elements. Now 4 is less than equal to 5. In that, this pair will be 4, 5. Now we will try to draw your 4 on the bottom part and 5 will be drawn on the topmost part. And there will be edge between this 4 and 5. Your 5 is less than equal to 6. Then 5 to 6 edge will be drawn. your 6 is less than equal to 7, then edge from 6 to 7 will be drawn. In that, 6 will be on the bottom part and 7 will be on the topmost part. We will start to write the smallest element of relation on the bottom part and the largest element on the topmost part. Why? Because our relation is less than equal to. Next format, let's revise another example where our set element is 1, 2, 3, 4, 5, where there exists a relation of division. Meaning of that means there are order pair A comma B such that B is divisible by A. Now to draw this Hasse diagram for this, what we will do, we will try to draw each point one at a time. Now your smallest element, first element is 1. 1 is divisible by 1, so we will just keep 1 point as it is. Now we will try to compare this element with another element of your set. 1 is 1 and 2. Now in that, 2 is divisible by 1, so we will draw arrow between this 2 and 1 where 2 is present on the top part and 1 is present on the bottom part. Now next element is 3. Whether 3 is divisible by 2? No, 3 is not divisible by 2. So what we will do? The main thing while drawing this Hasse diagram is always try to write your new number on the topmost level of your hierarchy. So we have created till these 2 levels of our diagram, vertex till 2 level of vertex from bottom to top. Now we are trying to write 3 at this part, but 3 cannot be divisible by 2. So we will again check whether 3 is divisible by 1. So if your element is not having any relation on the topmost hierarchy, try to relate it with the next lower level hierarchy element. So we'll check whether 3 is divisible by 1. Yes, so 3 is divisible by 1, so we'll draw 3 here. Now we will check for the next element. The next element is 4. Now 4, we will try to write 4 on the topmost part of your hierarchy. So we will check here whether 4 is divisible by 2. Yes, so this connection is existed. Whether 4 is divisible by 3. No, so this line will not be present. So our diagram till this is this. Now next element is 5. Our Hasse diagram is this: 1, 2, 3 and 4. Now we will try to write next element, that is 5. Whether 5 is divisible by 4? No. Whether 5 is divisible by 3? No. Whether 5 is divisible by 2? No. So only one element is left on the bottom hierarchy, that is 1. So whether 5 is divisible by 1? Yes. So our new diagram will be 1, 2, 4 and 3, and your 5 is divisible by 1. So this is our Hasse diagram for the relation. The next way is when your relation diagram is given but your relation or operator which exists on that relation which is not given. So how to draw Hasse diagram for such kind of diagram? First, what we will do here, our diagram is given. Now we have to convert it into the Hasse diagram. So we will try to check the bottommost point. That will be the point or vertex in which there is no edge coming from other vertex to that vertex. So this is the vertex where the edge is not coming from other vertex. All the edges are going from that vertex. So this is the bottom part of my diagram. So this will be present at the bottommost part of my Hasse diagram. Okay. And the topmost point will be the point or vertex through which there is no edge going or which is meeting to other vertex. All these edges are coming back to your vertex P. The edge is not going to any other vertex. So this will be my topmost element. So we have just kept the bottom part of your Hasse diagram and topmost part of your Hasse diagram. So K is bottom part and P is your topmost part of your Hasse diagram. Now after that, what we will do, we will try to check how many edges are present in between other vertex. K will be on the bottom part, P will be on the topmost part. Now from K to other vertex, how many edges are going to that vertex? Like for M and L, how many incoming edges they are receiving from other vertex? If they are receiving one incoming edge from other vertex, then they will be present on the next hierarchy. From K to M, there is only one edge is going. So I will place M on the upper part of K on this hierarchy. L is having one edge coming from K. So I will keep both M and L on this second hierarchy. This is my bottom part. This will be my next level. Now after that we are having vertex N. Again for this vertex, as there are two edges coming from different vertexes, so instead of keeping N here, what we have did, we have kept our N vertex on the topmost part of these two vertexes, because here one edge is coming to this vertex from other vertex, and for this vertex there are two incoming edges. It is receiving two incoming edges from other vertexes, so this will be kept at the next level, second level. This is for at first level, and this is at 0th level or bottom level. Now next point, that is P. For P there are 1 2 3 4 4 incoming edges are received from other vertexes, so that will be kept on the bottom on the topmost part of this vertex N. So this will be my diagram. So what you have to do now, whatever diagram you have drawn, so you just have to remove all the arrows, all the edges, and convert it into the single line. So just keep K to M connection, M to N connection, N to P, L to P, and K to L. Why I have not drawn arrow from K to N? Because if I will draw this will become transitive edge. There exists a path which is going in upward direction from K to N. There exists that particular edge. So this is not drawn. Since this is our last diagram, and this is our Hasse diagram. The next thing is, what are the elements of your poset partial order relation? What are the things you will have for your Hasse diagram? There are maximal element, minimal element, greatest element, and least element. Maximal element are an element A in the poset is called maximal if no element B in your set exists such that there exists a relation A which is less than equal to B. Then that element will be called as a maximum. And from all the maximum element, the unique, if you are having only one unique maximal element, then that will be called as a greatest element. For example, here in this Hasse diagram, we can say there is no element which is present on the topmost hierarchy of my G with which I can compare this relation, whatever relation. In simple word, we can see on the topmost hierarchy of G there doesn't exist any element. So this is my maximal element. Again for H, we are not having any edge which is going in upward direction and connecting to the other vertex. So this is my maximal element. Again for I, the same. No edge is going in the upward direction and meeting to other vertex. So this is my maximal element. In the opposite way, what we can say, if your vertex is not receiving any edge which is coming from bottom part, so that element will be minimal element. Now this edge is having no incoming edge. Again this vertex is not having any incoming edge. Again this vertex is not having any incoming edge. So this is my minimal element. For example, this element is receiving any edge which is coming from bottom part and edge which is going to above part. So this will not be considered either minimal or maximal. So these are my minimal elements for this diagram, and maximal element will be G, H, I. Now all these elements are different. There is no single element which is maximal element. So there will be no greatest element for this Hasse diagram. In the same way, there will be no least element for this Hasse diagram. For another Hasse diagram, this element is having no edge which is going in upward direction and meeting to any other vertex. So this will be the this is the vertex which is present on the topmost hierarchy while comparing from bottom to upward direction. So this is my maximal element. Again, in all the maximal element, there is only one maximal element. So this is my greatest element. Again for this diagram, there is only one minimal element. So that element will be the least element. For this Hasse diagram, A and B will be minimal element because no edge is coming to A and B. And H will be your greatest element because no edge is going from H and meeting to other vertex in upward direction. Lower bound, upper bound, greatest lower bound or infimum, least upper bound or supremum. Now here we have given with this Hasse diagram. Now all this lower bound, upper bound, greatest lower bound and least upper bound are used to calculate a subset, are used to find the bounds for your subsets. We never go for checking for each and every element of your diagram. We just always keep two or more than two elements in your Hasse diagram. We check all of these elements with the sets. Now first set is that B1 is a comma b. Now we have to find all these four elements. Now for a comma b pair, what will be the lower bound? We will take a comma b vertex. Now for a comma b, what I have to check, what are the lower bounds? Lower bounds are the point through which there exists path which is going to both these vertices. Like there exists a vertex which is present below these two vertex, and the edge is coming to both these vertex from that particular vertex. But there is no vertex which is providing edge to both the vertex and which is present in the bottom part. So there will be no element which is lower bound of my AB. Upper bound in the opposite way is that their upper bound is the vertex which are present on the upper part of your this set elements, and there exists edge which is going in the upward direction from all the set elements. Here my set elements are, or subset element are AB. For AB, I should have edge which is going and meeting in upward direction to at least one particular vertex. So here I am having vertex C, and which is receiving edge in the upward direction. While traveling in the upward direction, I am not having feasibility that I should go in the downward direction. I should travel to only upward direction. Now from starting with A and B, so if I will start to travel from A in upward direction, I can meet to C. Again from B, if I start to travel from B and to try to go in upward direction, I can meet to C. Means from both A and B there exists a path which is going in upward direction and meeting to one particular vertex. So that will be your upper bound. This is one of the upper bound. Again we have to check, is there any other vertex present from which you can reach from B, from all the subset points to that particular vertex. Again, if I will try to start my journey from A, I can go to E in upward direction. Again, if I will try to start my journey from B, I can go to reach. I can reach to vertex E in upward direction. So E will be my upper bound. In the same way, from both A and B, I have path in the upward direction which is going to D. From A to B, path which is going in upward direction and meeting to G, F and H. So all these elements are my upper bound. So C, D, E, F, G, H are my upper bound. Now if you are having some lower bounds, and in that the greatest lower bound can be found such that for all of this subset element, which one will be the nearest vertex, or we can say the vertex which is having less number of edges while traveling to that particular subset, then that will be the greatest lower bound. But as there are no element present in the lower bound, so there will be no greatest lower bound. In upper bound, we are having D, E, C, G, F and H. All these are my upper bound for A and B, which is present on the above hierarchy of my AB point. From all of this, which one is the closest one for A and B? That will be your least upper bound, LUB. Now for A and B, the path which is shortest, which is going in upward direction, that will be for vertex C. So C is a kind of vertex which is very near to my both of these vertex. Whatever subset I have given with, for all of these elements, this point is very closest point or nearest point in the which is present on the uppermost hierarchy. So this will be my least upper bound. So this is my LUB for subset A and B. In the same way, if we'll try to calculate this for set CDE, for subset CDE, what will be the lower bound? For C, D and E, what are the elements which are present from what particular vertex you can go and reach to this particular vertex, all of this vertex. From C there exists a path which is going and meeting to C itself. Okay, then C will be your lower bound. From C I can go to E, from C I can go to D. So this will be your lower bound. Again from A I can go to C, to E and D, means from point A I can reach to all the subset elements, then that will be my lower bound. Now for point B, if I will take point B, from B I am having again path which is going till all these elements C, D, E, then this is also my lower bound. Then your lower bound will be ABC. We have to find upper bound for this subset C, D, E. Now we should have element which is present on the upper hierarchy, and from all of these points there exists path which is going and meeting to that particular vertex. If I will consider whether, let's check whether D is upper bound of my this subset. Okay, then I should have path which is going from all of these vertex and reaching to that particular vertex. From C I am having path which is going and meeting to D. From D to D there exists a path. But from E I cannot go and meet to D while traveling only in upward direction. For meeting to D I will have to take downward direction. So this is not my upper bound. Again same with E. I can have path which is going from C to E, E to E, but there exists no path which is going in upward direction from D to E. So this is also not an upper bound of my subset C, D, E. Again we will check for vertex G whether G is my upper bound for subset C, D, E. From C there exists a path which is going in upward direction and meeting to G. Okay. From E there exists a path in upward direction. Okay. From D there exists a path in upward direction and meeting to G. Means for all the subset element there exists a path which is going in upward direction and meeting to that point. Then this point is my upper bound. In the same way F is also upper bound and H is also upper bound. So upper bound for this subset C, D, E is your F, G, H. Now we have to calculate what are the lower bound and upper bound of your subset C, D, E. We have to calculate among all of these lower bound what will be the element which is greatest lower bound. Means simple word, what is the element which is very nearer or closest to all of these lower bounds. For C, D and E, the element from A, C, E or element from all the lower bound, the nearest element will be C. So means time to travel from C to all of these element among C, A and B will be shortest. So this will be my greatest lower bound. And from upper bound F, G, H, time to travel to F, G and H. From this I can reach to F, I can reach to G, but there are two elements are present. From all of this I can reach to H. So this will be the element which is least upper bound. Why I have not considered both of this element? Because your least upper bound is only single element. Least upper bound for my subset C, D, E. Now we have to find the least upper bound and greatest lower bound for this subset 6, 7, 10. For 6, 7 and 10, what are the vertexes which are going in upward direction? Like this is a vertex which is present on the uppermost hierarchy, and from 6, 7, 10 there exists a path which is going in upward direction and meeting to 11. So this is my upper bound. And from all the upper bounds only this is single upper bound present. So this is my greatest, this is my least upper bound. Now for lower bound I am having element from which there exists a path which is going in upward direction and meeting to all of the subset element. Now there are this, from 3 I can go to 6, I can go to 10, but I cannot go to 7 in upward direction. So this is not my lower bound. From 1 I can go to meet 6, I can go to meet 10 and I can go to meet 7 in upward direction. So this is my lower bound. From 4 also there exists a path which is going in upward direction and meeting to all of the subset. So my lower bound will be 1 and 4. and from all of this I should have a common element which is providing a path which is lowest, or we can say which is greatest among all of this lower bound, then that will be your greatest lower bound. So for the path which is very closer from 1 and 4, which is very closer to your 6, 7 and 10, and that is only one element, so that is 4. So this is my greatest lower bound for this diagram. A lattice is a partially ordered set in which for each and every pair of element there has both least upper bound and greatest lower bound in your Hasse diagram, then that Hasse diagram is called as lattice. For simplicity, if we will try to take any age, for any age a comma b, a is always your lower bound, greatest lower bound, and b is always your least upper bound for that particular point AB subset. So we should always consider 2 points or element from which they are not connected by any edge for finding whether that is your lattice or not. For this diagram, if you consider 2, 3, we should have element which is greatest lower bound. Now from 1 I can reach to 2 and 3, so this is my greatest lower bound, and from 2 to 3 there should be a point which is going in upward direction. There exists a path from 2 to 3 which is going in upward direction and meeting to some particular point. From 2 I can go to 5, from 3 also I can go to 5. So 5 is my upper bound, 6 is my upper bound, but from 5 and 6 which one is closest one to 2 and 3? And that should be only single element, so that is 5. So 5 is my least upper bound. As for 2 and 3 both GLB, greatest lower bound and least upper bound present. Now again for 5, 4 we will check whether there exists least upper bound and greatest lower bound. Yes, for this greatest lower bound is 3 and least upper bound is 6. For pair 5 and 1, whether there exists greatest lower bound and least upper bound. For 5 and 1, I am having 1 as the lowest element, means that will be greatest lower bound, and 5 will be my least upper bound. So 1 will be GLB and 5 will be my least upper bound. So for each and every pair of this element I am having least upper bound and greatest lower bound. So this is my lattice. This is a lattice. Again this is a lattice. This is also lattice. This is also lattice. This is not lattice. Why? Because for these two, for pair of E and F, I am having greatest lower bound, the point which is having path which is going to both E and F in upward direction. Okay, but from E to F I am not having any element which is present on the above hierarchy of both of this E and F, and also from that point I will determine whether that point is greater or not. For this diagram, for E and F there exists greatest lower bound, but I am not having any single point which is present on the above hierarchy of E and F, and which will be from all the upper bounds which will be my least upper bound. So there doesn't exist any point, so this is not a lattice. Again this is not a lattice. Why? Because for example in this point for S, Q and R, if I will take this subset, for this subset I cannot determine which one is my greatest lower bound. I cannot determine from Q and R which one is the greatest lower bound. So this will not be my lattice. Again this is not a lattice. For point 4 and 3 I will not determine, I will not be able to check from which vertex will be my greatest lower which vertex is my least upper bound. So this is not a lattice. So this was about the lattice. Next topic is chain and anti-chain. Chain is any partially ordered set in which any two elements, any subset in which any two elements are distinct elements and which are comparable, then that is called as a chain. And anti-chain is the subset in which any two elements are not comparable or they are incomparable, then such subset is called as an anti-chain. In simple words, we can say chain is a line which is going from bottom part to the uppermost vertex, and in that we are having a path which is just going in a upward direction. In between, we are not traveling in downward direction from any point. So such subset or such sub diagrams we have to create. Then that point subset, the subset of that point will be called as a chain. Now this is my chain. This path is going in upward direction. Again, if I will start with P and if I will travel to S, this path is going in upward direction. So this is my chain. P, Q, S is my chain. Again, if I will start to travel from P to Q, Q to S, I am going in upward direction, but to include vertex R, I have to come to visit vertex R in downward direction. So this is not according to our consideration. So this is not a chain. For anti-chain, in simple word, we can say from your Hasse diagram, if any two vertex is not connected by any edge, then there are the chances that they are possibly anti-chain. Or what we can say, suppose I have to find a path which is going from Q to R, which should be in upward direction. From Q to R, whether I can reach from Q to R, which is having a path only which is going in only upward direction. Okay, if I will start with Q to S and S to R, I have to come in downward direction. This is not the possibility. Again, if I will start with P, I can go to Q, but I cannot go to R. Again, for reaching to R from any other vertex, I have to go in the downward direction. So this is not also possibility. So means there doesn't exist a path in between Q and R which is just going in upward direction and meeting to both the vertices at the same time. So this is anti-chain. These are some examples of chain. For this diagram, longest chain will be having 1, 2, 3 edges. So the element of your longest chain will be of 4 element, and the size will be the number of element present in that chain. That will be your size of your longest chain. So the longest chain is of size 4. For here, for these elements, these are the anti-chains which are drawn in the red color. So the longest anti-chain is consisting of subset which is having 3 elements. So the size of longest anti-chain is 3.